When we look up at the night sky, we often feel a sense of awe and wonder. The twinkling stars and the vast expanse above us can make us ponder our place in the cosmos. The vastness of space, sprinkled with stars and galaxies, can evoke a feeling of peace and tranquility. It's a serene sight that makes us believe in the calmness of the universe. It's easy to imagine the universe as a perfectly balanced system, operating in harmony for all eternity. The celestial bodies move in a dance that seems timeless and flawless. But is this truly the case? Is the universe really as harmonious as it appears? Despite appearances, the universe is far from balanced. Cataclysmic events like supernovae and galaxy collisions reveal a more chaotic reality. It is a place of constant change, with forces interacting in complex and often unpredictable ways. Gravitational waves ripple through space-time, altering the fabric of the cosmos. From the largest galactic structures to the smallest subatomic particles, imbalance is woven into the fabric of the cosmos. Even at the quantum level, particles collide and interact in unpredictable manners. This begs the question, why is the universe out of balance? Scientists continue to explore and seek answers, delving into the mysteries of black holes and the fundamental forces that govern our universe. To understand the universe's inherent imbalance, we need to rewind the cosmic clock to its very beginning, the Big Bang. This monumental event marks the birth of everything we know, from the smallest particles to the vast galaxies. This event, approximately 13.8 billion years ago, was not a neat and orderly affair. Instead, it was a cataclysmic explosion that defies our imagination. It was an explosion of unimaginable energy and density, a chaotic burst that set the stage for an uneven distribution of matter and energy from the very start. The sheer intensity of this event is beyond our current understanding. In the first fleeting moments after the Big Bang, the universe was a hot, dense soup of elementary particles. These particles were in a state of constant, frenetic motion, colliding and interacting in a high-energy environment. As the universe expanded and cooled, these particles began to interact and form the building blocks of matter as we know it. This cooling process allowed for the formation of protons, neutrons, and electrons, which are the fundamental components of atoms. However, this process was far from uniform. The distribution of particles was uneven, leading to areas of varying density and energy. Slight fluctuations in energy density in the early universe led to regions with slightly more or less matter. These tiny variations were crucial in shaping the future structure of the cosmos. These seemingly insignificant differences would have profound consequences over cosmic timescales. Over billions of years, these small fluctuations would grow and evolve, leading to the complex structures we see today. The areas with slightly more matter exerted a slightly stronger gravitational pull, attracting even more matter from their surroundings. This gravitational attraction caused matter to clump together, forming the seeds of future stars and galaxies. This process, known as gravitational collapse, is what eventually led to the formation of stars, galaxies, and the large-scale structures we observe in the universe today. Without these initial fluctuations, the universe would be a very different place. The Big Bang, in its chaotic beginnings, laid the foundation for a universe inherently prone to clumping and irregularity. This inherent chaos is what has given rise to the rich and diverse cosmos we are a part of. One of the most fundamental questions about the universe's imbalance revolves around the very nature of matter itself. This question has puzzled scientists and astronomers for decades, leading to numerous theories and experiments aimed at uncovering the truth. According to our current understanding of particle physics, for every particle of matter, there exists an antiparticle with the opposite charge. These pairs are like mirror images, identical in mass but opposite in charge, and they play a crucial role in the fabric of our universe. When matter and antimatter meet, they annihilate each other in a burst of energy. This process is incredibly efficient, converting the mass of the particles directly into energy, as described by Einstein's famous equation, E·mc². In the early universe, shortly after the Big Bang, equal amounts of matter and antimatter should have been created. This balance was expected to result in a universe filled with energy, devoid of any substantial matter. This presents a major puzzle. If matter and antimatter annihilate each other upon contact, why is there any matter left in the universe at all? The existence of galaxies, stars, planets, and even life itself suggests that something tipped the balance in favor of matter. Shouldn't the universe be filled with nothing but energy? This question challenges our understanding of the early universe and the fundamental forces that shaped it. This is the mystery of the matter-antimatter asymmetry, one of the biggest unsolved problems in physics. Understanding this asymmetry could unlock new insights into the very nature of reality. Somehow, a tiny excess of matter, roughly one extra particle of matter for every billion pairs of matter and antimatter, must have survived the early universe's annihilation frenzy. This minuscule imbalance was enough to seed the formation of all the structures we observe in the cosmos today. This slight imbalance, though seemingly insignificant, is what allowed for the formation of stars, planets, and ultimately, life itself. Without this tiny excess, the universe would be a vastly different place, likely devoid of the complex structures we see. The exact mechanism that tipped the scales in favor of matter is still unknown. Researchers are exploring various theories and conducting experiments to uncover the processes that led to this crucial imbalance. However, scientists believe that subtle differences in the behavior of matter and antimatter, known as CP violation, may hold the key to understanding this crucial cosmic imbalance. CP violation refers to the slight differences in the laws of physics that apply to particles and their antiparticles, which could explain why matter prevailed. Unraveling this mystery is crucial to understanding not only the evolution of the universe, but also the fundamental laws of physics themselves. By studying this cosmic imbalance, we hope to gain deeper insights into the origins and fate of the universe, and perhaps even discover new physics beyond our current theories.